Ladies and gentlemen, welcome. Today in our online industry tutorial, we host the Explorer Introduction to Photonic Integrated Circuits session that is part of the PIC Bootcamp program. I'm John Pugh, Director of PIC and Quantum Technologies at Optica, and I'm very pleased today to welcome Cornerstone, a UK-based open-source, license-free silicon photonics prototyping foundry, specializing in manufacturing photonic integrated circuits, or PICs, for high-tech sectors such as telecoms, sensing, quantum technologies, LiDAR, and many more. In the first half of today's tutorial, we'll hear from Professor Callum Littlejohns, Deputy Director of Cornerstone, who will deliver an accessible technical introduction that highlights the unique benefits of PICs. Remember, this is an interactive event. We have over 800 people registered, so please ask your questions in the chat and the Q&A Zoom facility, and we'll do our best to address them at the end of Callum's presentation in the panel session that follows. Callum, you're already sharing your slides, and the floor and the attention of everyone is yours.
Okay, welcome everybody. Thank you very much, John, for the introduction. Thanks everybody for joining, myself and my fellow panel members for the next hour. As John has explained, the intention of this webinar is to introduce the technology of photonic integrated circuits. I will explain the concept of how it works. We'll go through a number of application areas where it's already having huge impact. And then towards the end, we will explore some of the remaining challenges for the technology and look at the current and future trends that we're seeing in the field. As John said, this is part of the PIC Bootcamp program for which the partners involved shown in the top of the slide. First, I'd like to say thank you to the people and the teams listed on this slide who have contributed to some of the content throughout. So let's start. What is a photonic integrated circuit? First thing to say is the little clip that you're looking at is not a photonic integrated circuit. It's, shall we say, an artist's impression of what one looks like. So visually, at least at low resolution, it looks like a semiconductor chip that you're very likely very familiar with from electronics chips. But instead of using electrons, we are using the technology of light or photons. And the reasons that we might choose to do that, I will cover in the subsequent slides, and we can discuss later in the panel session. This is probably my most technical of all of the slides. I just thought it'd be worth introducing the fundamental concept of how a photonic integrated circuit works. So what we're looking at here is a cross section of the main fundamental building block of a photonic chip called a waveguide, and it's a device that routes light around a chip. If you compare to or analogous to the electronics domain, this is like a metallic wire, for example. Metallic wires will transmit electrons, and a photonic waveguide will transmit photons. And it does it using a process called, or a concept known as total internal reflection. And what that means is that if we have light of a particular wavelength in a material of a higher refractive index, when this light reaches an interface with a material with a lower refractive index, in this case silicon dioxide, if that light is incident above a certain angle called the critical angle, we achieve a reflection rather than a transmission of the light through the interface. And you can see how this concept, if we propagate, say, into the screen in this example, we can build a device that continuously reflects the light and confines it within the waveguide. So here we have a silicon layer. On the y-axis, it's sandwiched between two silicon dioxide layers. On the x-axis, we can see that we've created this geometry where the silicon layer has been partially etched, and that provides our confinement in the x-axis of what we're looking at here. On the right hand side, you can see the simulated electric field profile of a optical wave of a certain wavelength, and as you can see that the power is confined within the waveguiding region, and if we extend this into the screen, it will then guide the light around the chip. Using this fundamental building block, we can build more complex circuits. Again, if I compare to electronics that might have building blocks like a transistor and a diode and resistor, similarly in photonics we have things like optical couplers, power splitters, resonant devices, and interferometer devices. And we can stitch these individual components together to build very complex circuits that perform lots of different operations for a whole host of different applications. But it doesn't work as a standalone system. We also interact with the electronics domain. So there are three key devices that enable this to happen. The first being a light source, or in this case, a laser. That's where the optical signal is generated that then propagates throughout the circuit. If we then want to encode an electronic signal onto that optical signal, that's done using a device called a modulator. And there are a whole host of different means of achieving this, but we won't go into the detail of that today. And then at the other end of your circuit, once you've transmitted and done some optical operations on your signal, you'll typically need to convert it back into electronic signal for further processing. And this is done using a device called a photodetector. So the combination of all of these different components means that we can interact optical and electronic signals. Why would we want to do that? This slide, at a very high level, attempts to pick out some of the key benefits of the technology. And number one, in terms of adoption of new technologies, cost is obviously a key factor. And the reason I put cost at the top, and this is somewhat specific to silicon photonics in particular, because we are using the same manufacturing techniques and in many cases the same infrastructure as the electronics ecosystem, we know that we can manufacture these things at huge volumes with high reliability and high stability. And ultimately, at these high volumes, that leads to a very cost-effective price per millimeter square. That's where silicon, as opposed to other different platforms with integrated photonics that I'll come on to in a minute, I think that's where silicon is particularly interesting, because we've got this huge global ecosystem of expertise in silicon manufacturing. Coming back to PICs in general, if we compare to bulk optics, a key selling point is obviously that we can shrink things down, we can make them smaller and lighter, and you can see for applications like space, satellites, this is of key interest. And the third and the fourth bullet points here, I believe, are two of the main reasons why we've seen a massive boom in the technology of silicon photonics over the past couple of years. And that's because using light instead of electricity, we can transmit data at extremely high bandwidths and critically with low power. We all know about the huge increase in demand for data that's brought around because of AI. And that comes at a cost in terms of energy consumption. So it's absolutely critical that operations in a data center become more energy efficient, so that we don't need to build a load of new power stations. And that's where the movement from transmitting data in the electronics domain into the optical domain is of huge benefit. You've probably seen NVIDIA are active in the space. They claim that they can save 3.5 times the amount of power so 3.5 times less power when transmitting high volumes, high bandwidth optical data relative to electronics. Looking at some of the applications, I focused to begin with on data centers and transceivers, and that's definitely the largest and most successful commercial silicon photonics success story to date. It's been deployed for at least a decade now, but the interest has massively increased in the past couple of years, driven through AI. And this is typically a transceiver type device that's embedded into a data center. What we're looking at on this slide, this is a photograph of this here is a photonic chip. I'm not sure if you can see my mouse or not, but on top we've got two electronics driver chips that flip chipped on top of a silicon modulator. And I'll come on to that, but that's definitely a direction of travel that we're seeing more and more integration of different chiplets, different materials onto silicon. So whilst data centers is the leading commercial application right now, there are a whole host of emerging applications, and in some cases emerged, I would say, where the benefits I've already touched on also apply. And one of such use cases is LiDAR. Pleased to be joined by Remus Nicolaescu on the panel session later, who's the managing director of one of the leaders in the field of integrated photonics LiDAR systems, Pointcloud. Any questions you have about the technology in that sector, I encourage you to direct towards Remus later on. Sensing is another hugely exciting opportunity for the field, and it's absolutely a massive growth area. And that covers different domains like health technologies, environmental sensing, and defense. And here in particular, I think, particularly for health, where we might want disposable chips, the ability to manufacture things at huge scale and therefore low cost per chip is obviously of huge interest. And photonics can give you highly sensitive sensors that have a whole host of different applications across many of the sectors, including those listed on the slide. There are many applications. I don't want to go through all of them today. So one more where integrated photonics is prevalent is in quantum technologies. The ability to transmit and manipulate and generate quantum signals at room temperature, coupled with the knowledge that we can scale semiconductor devices to huge volumes with high precision, makes it one of the more compelling approaches to building a useful quantum computer and other quantum technologies. So the message I'm trying to get across here is that silicon photonics and integrated photonics is very much here and now. There are a whole host of applications of varying degrees of maturity and adoption, but the risk to entering the field is significantly lower today than it was even 2 or 3 years ago, because the whole ecosystem has massively evolved. This slide I borrowed from Photon Delta in the Netherlands, shows a snapshot of some companies, just highlighting this is not intended to be exhaustive, showing some companies who are working across these sectors. And whilst it's fair to say that most of them shown on this slide are startups and SMEs, it's absolutely clear that it's not a technology that's exclusively in that domain. If you look at the top 10 most valuable companies as of today across the world, actually all of the top 8 have active programs in silicon photonics, and this ranges from R&D programs all the way up to deployment in their infrastructure and across the world. So again, like the ecosystem is massively evolved. It's gaining maturity rapidly, and there is widespread adoption, diversification of the technology. So it's no longer dominated by academia. There are now the world's biggest companies, a diverse range of startups and SMEs, and broad-ranging research activities in academia all across the world, benefiting and exploiting this technology. And silicon photonics and integrated photonics in general no longer means just silicon. If we go back 15 years, when we said the word silicon photonics, it generally meant that most of the operations were in the material of silicon. That's now changing, although silicon-based technologies are definitely the most mature and the easiest to access at larger volumes, but we are seeing a diversification of platforms, an introduction of new materials, in many cases still on a silicon substrate. Why are we doing that? This slide that I borrowed from Light Trace Photonics shows the transparency of different material platforms at various wavelengths. And we're all familiar with telecom wavelengths, where the field has really started. But some of the applications I mentioned require or are better performing at different wavelengths where silicon may no longer be transparent. So we have to move to different material platforms to enable us to build waveguides that are transparent at their wavelength of choice. There are many other reasons or considerations that you should use when deciding what material platform is right for you. And just to pick out a few examples, silicon nitride is a very good passive material, so it can give you much lower optical propagation loss relative to silicon. The downside to this platform is it doesn't have any active functions like modulators and photodetectors, so you require integration of other materials. And then one more example, TFLN, which is thin film lithium niobate. That's gaining a huge amount of momentum in the last few years. The reason for that is it overcomes some of the limitations of silicon-based modulators. We can build faster, generally speaking, slightly faster optical modulators, but the key improvement is in the loss. So silicon as a material, at least with the most conventional modulation mechanisms, has a loss penalty that we can avoid, where when we create our modulator, we also introduce a fairly high insertion loss of the device, and introducing other materials like thin film lithium niobate can overcome this. So we can have high speed modulators without the associated loss. If you're feeling a bit overwhelmed, there are so many different platforms, how could you possibly choose? I encourage you to reach out to parts of the ecosystem. Like in Europe, there's a group called FhCAP that bring together a whole consortium of different members. They can help guide your choices on which material platform might be right for you. But also you can talk to the software houses like this, or the software companies. This slide, again, not intended to be exhaustive, shows a snapshot of some of the companies who provide design software for you to do component design, circuit design, circuit layouts, and design services. So a design service or design house might be a good place to start to help understand which material platform is best suited to your application. And again, like the message throughout my presentation is that this is a rapidly evolving area. Maturity is increasing every year. These tools, the Foundries, are getting more and more mature and higher quality with additional functionality. Now I'm going to introduce a process design kit. Many of you are probably familiar with what this is. But it's, as a designer, it's your key tool to engage with the wider ecosystem. But typically, the manufacturing facilities or foundries will own process design kits, the packaging houses similarly. And these are tools that will communicate to you as a designer all of the information you need to be able to design into any given platform. So the types of things contained in a process design kit will be layer thicknesses, the optical and electrical properties of the different material layers, the minimum feature sizes that are possible to achieve for your circuits. And crucially, most of the time, they will contain building block components that the foundries or the design houses have designed and validated in their particular platform. So this is an extremely valuable tool, particularly to people new to the field, where you can take known performance building blocks, stitch them together, and this massively de-risks your entry into the technology area, and hopefully also speeds up your route to market by shortening the product development life cycle, because you're working with known performance devices from the outset. And then once you've designed your chip, where can you get it made? This is, I think, in this case, a bit more complete list of the silicon photonics foundries that are accessible across the world. You can see they're focused in North America, Europe, and Asia. And these facilities range from R&D, university-based rapid prototyping services through to the scale-up research organizations, all the way through to mass manufacturing. You can see most of the famous, well-known leaders in semiconductor manufacturing listed here are now adopting and deploying or enabling access to silicon photonics technologies in their respective platforms. So the choice is broad and far-reaching. This gives you a diversity of different options. It gives you some supply chain resilience as well. And I do just have one single slide on Cornerstone, since that's where I work. We are a rapid prototyping facility hosted by the universities of Southampton and Glasgow in the UK. We specialize in rapid prototyping of a whole wide range of different material platforms. We are very proud to be, I think, the only open source facility where we openly publish all of our process design kits. We believe this massively reduces the barrier to entry. We have all of these different platforms because, as I've already hinted at, depending on your application will affect the platform of choice for you. So we try to enable access to a whole host of different technologies so that we can serve whatever your requirements are. If you want to know more, please visit the Cornerstone website. Then once you've got your chip made, obviously that's only part of the overall system. So you'll likely want to engage with a packaging house. And again, I've shown a snapshot of some of your choices, different parts of the world. Again, same message, sound like a broken record, but this is rapidly evolving. Most of these companies will have very mature processes that you can access. They are very much used to working with photonic chips. They're used to taking photonic chips from various different foundries and packaging them for you. So the risk and the barrier for you to get into the field is now much more streamlined than it was, say, 5 or 10 years ago, where the ecosystem wasn't quite as mature. What might a business model look like for a company or working in the technology area? It's fair to say that the fabless model is widespread. So that's where you as a company your IP and know-how is in the design and the system level. Typically, you would outsource the manufacturing to often multiple partners that specialize in their respective areas. And this means that you don't have the huge upfront capital costs required to build the infrastructure needed to to manufacture these chips. You can focus on specializing in design and working with various partners to do the fabrication work. And these different partners, their specialisms in the manufacturing. So it's a win-win environment. If you're wondering what it costs, obviously it depends on the platform and the complexity. So some very generic rule of thumb foundry prices. The entry level, what's called multi-project wafer. So this is a cost sharing mechanism where you buy a small number of chips on a big wafer, but it's shared with other users. The typical cost of this might be in the thousands of dollars per millimeter square. But as we've seen from both the electronics industry and from the transceiver market in photonics, as volumes increase, the cost per unit area will massively reduce. So once we reach high volumes, the cost per unit area can be as low as $1 per millimeter square. And a typical IP approach is that you as a designer retain your design IP, the manufacturing or packaging partners retain their manufacturing IP. It's worth pointing out that most foundries and packaging houses will have their components will be in IP black boxes, so you're likely to require a license agreement to access the IP in their building blocks. I'm running short of time, so I'll just whistle through two examples of devices. This is some work from my colleagues in the University of Southampton, the research group, showing, to the best of my knowledge, the fastest silicon photonics or all silicon modulator of a particular device configuration. We can demonstrate 200 gigabaud or 200 gigabit per second data streams generated in an all silicon solution. And like I've already said, like the appeal of this compared to say an electronic signal is that we can save NVIDIA's marketing says about 3.5 times the power consumption. Changing entirely to a different area, what does a biosensor look like? This is a cartoon of very simplified cartoon of how it might work. On the left-hand side, we've got our light source. On the right, we have a detector. And in the middle, we have an area where the environment is exposed to the top of our photonic chip. And by functionalizing certain areas of this device, we can make it highly sensitive and specific to a given analyte. So by propagating light through this circuit and measuring the output, we can detect with high specificity the concentration of any given analyte that we're trying to detect. So this can be designed to detect gases, enzymes, cancer in some cases. So it serves a whole host of different applications. And what are some of the remaining challenges? I think the laser integration, the packaging still dominates the cost. And there is a challenge around optical alignment where it's much more difficult to align an optical fiber and a waveguide that it is electronics comparison, because we need to align the modes of the two different parts. That's usually done using an active alignment process where we actually propagate light through and measure the output and optimize for power. So that comes at a price in terms of how long does that take and how much does that cost. So there's definitely opportunity for innovation there. Can we get pluggable, more tolerant couplers? That's just one example. Another remaining challenge is around manufacturing tolerances. So whilst the photonic devices are much bigger than electronics counterparts, they're still highly sensitive to dimensional changes and indeed temperature. So there are still challenges and again, opportunity for innovation in building design aware and manufacturing aware, manufacturing tolerant designs where we can accommodate unavoidable tolerances in the manufacturing process in the design phase so that we can give ourselves like a better yield, more chance of success from early designs. So that is how can we shorten the product development life cycle? And I think understanding the limitations of the manufacturing process and accounting for that in design is a key way of achieving that. The current trends, there is now a move to integration of new materials on silicon, but also chiplets or so-called co-packaged optics. And what this means is that we are now integrating multiple chips that each specialize in a different function onto the same board. And that means we can, get the best of all worlds. In effect, we can design our electronics chip in a platform that is optimal. We can design our photonic chips over here in a different platform, and we can then stitch them together with some sort of interposer or whatever onto the same board. But what is absolutely critical here, and this is definitely a current trend, is that these things can't be designed in isolation and then plugged together. They absolutely need to be designed as a system. And that's where the software companies, that's where a lot of the ongoing efforts are to improve the system level modeling of how do we design these things as a system. We can account for electronics domain, the photonics domain, the mechanical and thermal, and all of that, all within the same package. I'm out of time, but I've only got, I think, 2 more slides here where I'm just showing, for example, in the modulator, where there is exploration of lots of different materials that overcome some of the limitations of silicon, but I don't have time to go through that in detail. As John said at the beginning, this is intended as an introduction to PICs. It is part of a bigger training program called PIC Bootcamp, where we cover different elements of the supply chain. So at the beginning, we look at characterization of PICs. We look at modeling PICs, laying out PICs in terms of the mask layout. Then we cover fabrication and PIC packaging. The dates for this year are shown on the slide along with the prices. This is modularized, so you can decide that you want to just come to 1 or 2 or multiple of the modules. It's up to you. Highly encourage you to come to them all. If you understand each of the constituent parts, it definitely makes you a better designer. If you happen to be from the UK, until next Friday, we are offering a buy one get one free for UK academia and SMEs, and this is leveraging some UK government funding that we have. If you want to know more, of course, everybody's welcome. Please visit picbootcamp.co.uk. So one last slide, then I promise I'll open the floor to the panel members. If you're interested in PICs, you're intrigued to know more, what should you do? These are some recommended actions. You can consider different approaches. So you can consider licensing approaches. There are design houses that have lots of building block components that you can go and license. You can pay them to do design for you. Absolutely start looking at different partners for not just design, but manufacturing as well. The foundries, the packaging houses. Consider training, and shout out again to the PIC Bootcamp scheme. The last point is just have a go. I would say the cost for doing a multi-project wafer run is relatively small. It's of the order of a few £1,000 or a few $1,000. So just have a go. Design a chip, have it taped out, and measure it. And that will help you to understand some of the challenges. It will help you to build partnerships. And hopefully that will be your gateway to adoption as a technology and an overall growth of the field as a whole. So thank you very much for listening. I will share my slides at the end with all the delegates. I've also got a load of slides I had to cut, and I've still gone over time. So I'll now stop sharing and hand over to John and the other panel members. So thanks a lot for listening.
Thanks so much, Callum. A really excellent overview. As Callum said, the slides will be shared to those of you asking in the chat, and more comprehensive, because I know Callum wanted to say so much more. Also, the video recording will be shared. So we've heard what PICs are, and Callum's said what the benefits are, and this panel discussion really builds on that and is about a simpler question: how do you decide whether PICs are actually right for you? And now it's time to address that and some questions from the audience. And to do that, I'd like to introduce you to two further expert panelists, and I'll try to weave in as many questions as time allows. So firstly, Dr. Remus Nicolaescu, CEO of Pointcloud, who are based in the San Francisco area with teams in Zurich, Switzerland, and Southampton, England. And also Sia Andersson, a senior researcher at the Fraunhofer Centre for Applied Photonics in Glasgow, Scotland. I'll ask the panelists now to briefly introduce themselves and their expertise in the area of PICs. I'll start with you, Remus.
Hi, everyone. So I'm Remus Nicolaescu, as John has already mentioned. I'm one of the co-founders of Pointcloud. Background, I started in silicon photonics 26 years ago at Intel in 2000, trying to design at the time what right now looks like incredibly slow modulators. 1 gigabit per second was the first one we did in 2001 or 2. And yeah, so I've been on and off in silicon photonics ever since. And currently we design at Pointcloud extremely complex circuits using both electronics and photonics, literally millions of transistors and silicon photonics components on a chip for 3D imaging.
Thanks, Remus. And Sia?
Hi, I'm Sia Andersson. Indeed, I'm a senior researcher at the Fraunhofer Centre for Applied Photonics. We're based in Glasgow in the UK. I oversee and deliver our integrated photonics activities. I have about a decade of experience in the field. As Fraunhofer CAP, we work across all applications: quantum sensing, quantum computing, also comms, biosensing, and defense. And that's probably not an exhaustive list of all the applications we work on. We offer design, fabrication access, testing services. We work with the entire ecosystem, such as Cornerstone, and we're entirely platform and Foundry agnostic. So we sort of just solve everyone's problems where we can.
Great. Thanks, Sia. So let's jump in. So let's explore when a PIC kind of makes sense. What are the clearest signs that an application is a good fit for PICs? Or equally, what are the warning signs that a PIC is probably not the right solution, or at least not yet? Who would like to take that?
Suppose I can go first. We work across very different application areas. So I think from our experience, if you have an established setup or system, that can be a good starting point. If we can identify components or elements that can be translated to PIC. PICs are ideal if you need to scale up or you want to miniaturize to deal with size, weight, and power concerns. Even if you're not particularly concerned with swap, then if you want to scale up, scale out quickly, PICs are a good candidate. I think when you maybe don't want to go for PICs, if you're very tight on time or as accessible as it is in terms of cost, if you're wanting that peak performance, that usually involves, some iterative development. So as long as you're happy that your first prototype maybe doesn't hit all the marks, then that's fine. But if you need something that's going to be very, very quickly made, then that can be a challenge depending on your timescales. Depends on what is a short timescale for you, I suppose.
Yeah.
Would anyone like to add? Remus, please.
I can take a little bit sort of in addition to what Sia mentioned at higher level. So of course, in general, a large number of components, in most cases, I would say that in general, I would answer this question is it depends. So there are a number of parameters and there is no magic, like you check the box and it makes sense. It's more like there are a few things that you should look at and it might or might not make sense. And I would start with a large number of components. There is a good chance that you might be able to do better on an integrated solution than versus discretes. This is not rocket science. It's the same in the electronics industry. You can put components on a board or you can put them on a chip. And yeah, decent volume, similar to the electronics industry. So if you have volume, you design an ASIC. If you don't have volume, you don't. You do it on a board and kludge things together. Then there are a couple of things that are a little bit trickier. So reliability. In our space, we're quite often replacement for optomechanical systems. Solid state always beats optomechanical. So there might be reliability concerns on which a PIC might be a better solution. Then the other bit is certain performance characteristics. Again, in our case, we don't only do electronic photonics integration, we also do electronic photonic integration. So there are certain situations in which a discrete approach, in which you have the electronic components separate from the chip, might not get you the performance you need. The parasitics are too high. You just can't really reach the same level of performance versus when you're on a chip. So, I mean, I would probably say kind of these, but there is no magic formula. It's just you kind of look at these and you just kind of figure out whether for your application it makes sense or not.
Thanks for that. Do you want to add anything, Callum, to that? Or?
My fellow panel members have done a great job, but my view is that when you demand volume and scalability, that's where PICs are a clear winner choice up front. But I think on the more it's also about relationships as well. So if you're familiar and already in the ecosystem, it's just easier to start adopting it. So you need to leverage existing partnerships. It can be challenging to come into a new area when you have entirely new partnerships. But that's where you can leverage the support of design houses and places like the Fraunhofer. They will help you to make those choices on whether or not a photonic chip is the right choice for you.
Okay, great. So let's move on. So if someone's watching, they're not currently using PICs, and what does a sensible first project actually look like? Where do the first time PIC projects most commonly struggle? Is it kind of design, fabrication, packaging, or testing? And what parts of the PIC journey tend to be underestimated, would you say?
Maybe I'll start there because we as a founder, we often see this. For sure, the packaging and testing is often overlooked, and also an understanding of some of the limitations involved with the manufacturing process. So typically we might see a hugely complex circuit come to you for the first time that may or may not be successful, but in the design we don't have test structures to try to fault find where something might have not worked as you've anticipated. So it needs a lot of thought around how are you going to test this thing, how are you going to package it, and what are the limitations of the manufacturing. So I would say a first thing you can do is just have a go at a multi-project wafer run. Keep it simple to start with. Don't start with here's my finished thing, because it almost certainly won't work the first time.
I can only agree with what Callum is saying. Packaging and the testing is probably the questions you want to explore first, and then almost design backwards from there as to what you want to achieve. I think the other thing is just because there's a published paper on a technology, it doesn't necessarily mean that process is widely available, or that the performance you saw in a published paper can be accessed on a commercial volume scale right off the bat. Usually the sort of top results you see from big players, they've spent decades developing that. And if it's a published paper, then, well, you had a batch that worked really well. It doesn't mean that, anyone can spit that out from any foundry at any given time. So I think the management of fabrication processes is something that's underestimated. If foundries like Cornerstone put a lot of effort into really controlling their process, and they know it very well. But if you don't have that knowledge, you can't sort of rock up to a tool, press a button and get what you want immediately.
Remus, would you like to add to that? Or
So I can add a little bit of a more like industry perspective because we work
yeah,
with more mature processes. So in our case, we actually always had first time silicon right, but that's because we work on a commercial large scale process at global foundries. But so for us, that's a little bit less of an issue, but that comes with certain challenges because we work on standard tools, we work on as I said, on a large volume process. We do everything LBS, DRC clean before it goes into the foundry and all that stuff. So we play by the rules of the electronics industry, not only photonics. So I completely understand what Sia is saying and Callum is saying. I think for most foundries, everything they said is correct. The process is not robust enough that you can design and hope for first time silicon right. There are only a couple of foundries that I would dare to do that with. As far as what people would struggle with, I would say also that packaging is always a challenge. And I would also add to that, one of my least favorite things is whenever you have to integrate or have to deal with light source integration or any kind of more advanced performance like light source, if you have special requirements for the light source, like narrow line width or fast tunability or all sorts of things, anything, whenever you have to deal with 3.5s on integrating on anything, it's generally something that takes a lot longer than you think and is more painful. And then the last one is my favorite answer to pretty much all the questions. It really depends. So you can get yourself into trouble, as Callum said, with very high speed components, extreme miniaturization, you're pushing the limits. Things might not work as you thought they would. And finally, very low cost, which is kind of an all-encompassing thing on which you're pushing all limits and things eventually break. So,
sure. Well, thanks for that. I'm sure we have some very skilled workforces in other areas, maybe not PICs, watching today. In your experience, how should those teams, and how does it generally work? How should those teams think about combining that in-house capability with external partners or PIC design houses, like Callum said, for example? How does that kind of thing usually work?
I think it's useful to know the basics of PICs, even if you do end up relying on outside help. I think having sort of a really good understanding of the specs and their priorities relative to each other for your end system is something that helps a lot. So with that in mind, getting to peak performance, as Remus and Callum have suggested, it is a bit of an iterative engineering challenge that you have to conquer gradually. I think when developing a PIC approach, you might need a big team to get started, but the question would be long term, are you going to want to do all of this in-house, or is it just you want some sort of PIC that you do on a volume and you just keep repeating the same type of PIC? In that case, then it's probably good to reach out to something like a design house or an organization such as ourselves who can help with the R&D stage of it. So I think that's something to keep in mind. But you may want to own aspects of the process yourself. But yeah, the more you understand your own process and output, I think the better. By achieving that, you might want to turn to external partners to get started and do the development stage.
Perhaps I could add, like, if you're used to designing, say, for example, electronics, it's likely that the software packages you're familiar with now have photonic chip packages as well. So you can just engage with them and start with something you're familiar with. So you're not moving to an entirely new environment. You can absorb new modules of packages that you're already used to using. And all of the software providers give access to training in many cases at no cost. So just have a go, I would say.
Yeah, I'm probably going to bring again a slightly different perspective because we, as I said, we're a little bit more like industrial and all that. So for us, actually, the most sort of the important thing. And we actually don't really find people in the PIC coming with PIC background having this, but we try to just train people. It's sort of the IC design mindset. So we use standard tools. So we use the standard Cadence Virtuoso and Calibre and Pegasus and all the standard IC tools. We also have, because we have electronics and optics on the same chip, we have mixed signal designers, 20-year Intel veterans working with PIC designers on the same chip. And we try to get the PIC guys to work exactly in the same mindset with the same discipline as the IC industry. So we generally, of course, we like the idea of having people that are already trained on Cadence and Calibre or and Siemens tools. In reality, we don't really get those people in universities. Typically, at least at this point, people do not get trained in these tools. It's a lot of open source tools and things like this. But I think what is more important is operating with a high level of abstraction. We only redesign components when we have to. So as kind of like in the electronics industry, you don't redesign the transistor. TSMC does that. So we tend to work a lot with PDK components. We don't mess around unless we really have to with a component at a component level. And and then it's the whole thing with the RCLVS clean. No cutting corners and all that, because that generally is very expensive if you make a mistake. So I think that's kind of like what I see as sort of we're hoping at one point that also the photonics industry evolves towards that. So there is more standardization, there is more discipline, and yeah.
Sure. Motivated by a couple of questions in the chat from Ziad and Julia about heterogeneous integration, I'd like to talk a bit more about navigating the material landscape. So Callum touched on this very nicely, but Remus and Sia, in your experience, how do you navigate that choice of platforms? And especially in industry, some of those material platforms are much more mature than others. So how do you assess if there's a route to market with some of the more exotic materials? And maybe one of you can explain what heterogeneous integration means.
The trendy topic of the minute. When I started doing PICs, we were talking about monolithic integration, which is the opposite of that. So times do change. Heterogeneous integration is trying to bring the benefits of different platforms into the same chip or the same system. So you might use silicon nitride for its wide transparency window and say grating couplers, but you might want the fast modulation of a thin film lithium niobate or other electro-optic material platform. So I guess that brings me to, I think the choice of platform is quite strongly led by the application and the specifications you need. You need to consider that optical transparency window. Where are you wanting to work? Do you need tunability? Do you need modulation? How fast does it need to be? What does the wider system look like? So I don't think either that there's too many platforms, but as you mentioned, John, they're not all equally mature and accessible. So once you've identified what your dream platform would look like, I guess the question will be, can you actually access that and at what cost? So then the sort of reality hits and maybe limits your choice.
Sure. I think that's a fairly comprehensive answer to that question. So maybe I can move on. There's a question. I guess it is very application specific, but can you provide some figures, for a component of the same function? How much cheaper, smaller, lighter is a PIC compared to its electronics counterpart? Pick an example, maybe, and an estimate.
So you're looking at the optical component versus electronic component?
Yeah, and how much cheaper, possibly smaller and lighter, can it be made with a PIC?
Well, I don't think that's actually, that's kind of photonics wouldn't do very well compared to electronics because the transistor is way, way, way smaller than anything photonics. So I don't know. I don't know. Like the last chip, we put 0.6 million photonic components on a chip. That's whatever that is, 400 millimeters squared divided by that. But I don't think that's fair because we have way more transistors. So if it comes down to transistors, it's hard to beat electronics. because you have billions, so it's on the same area. So it's
Sure.
I think on a large scale, the operation might be, well, that's the thinking, right, with bringing PICs into data centers, is that the energy and cooling requirements will be much less, or they function quite happily at different temperatures. So it's sort of more of a long-term cost benefit. But size-wise, yeah, you can probably get the size of the overall system down. But yeah, as Remus says, it's quite it would be very specific to the system. If it's already an optical, like versus electronics, optical systems, when you incorporate PICs, you usually get a smaller size, a smaller footprint. But it depends.
I mean, in general, like the rule of thumb is optics is great for transmission, electronics is great for processing. So they do two different, very, very different things. So if you're looking, so compare like sizes, it doesn't really, there are two different functions. So, and I think also when you look at photonics, what it's trying to do is trying to replace discrete. So that's really where the difference is. So if you do packaging discrete components, the more interfaces you eliminate, the smaller it gets and the higher performance and cheaper. And then it's the speed. It's light transmits information much better than electrons.
Sure. And you've mentioned datacom and transceivers and things. I think that's really pulled PICs forward in terms of different materials, different applications. What can you see as the next big application of PICs? Remus, you obviously work with Pointclouds.
Yeah.
Would you say that is the next big application?
Well, we think it is, of course. Otherwise, we wouldn't do it.
Sure.
So I'll let the others answer because we're biased.
Well, I think it's things that go into consumer or have huge volumes, and LiDAR, you can see most people own a car, at least in many countries, so there's huge opportunities there. Sensing, I think, is a big area of growth, because actually in a sensor, the photonics chip's often actually quite simple. The challenges there are more on the chemistry and the biology side often. But those types of applications will demand massive volume. There are only so many data centers in the world. I know it's not constantly growing, but if you could have, envision disposable sensor chips, you can see opportunities for massive volumes there.
Yeah, I can maybe do a little plug here, but Callum, can I share something? Because Callum gave us one of those pictures you need to replace, Callum. That's like incredibly old and really terrible. Sorry. If you just go on our website, there are some new point clouds, and at this point, our devices work like cameras, so you can get an extremely nice point cloud with a camera-like device. And I'm trying to get to it. Yes. Like this is an example of a recent point cloud from like last month. It's like a team picture in the office. This is a fully solid state device. It's camera-like, so it's just a lens in front of the chip, and that's it.
That's incredibly impressive, Remus.
So much higher resolution, much higher accuracy. It's we'll have to talk, Callum, about you replacing that whole picture.
Yeah,
Sure.
I'll get it. I'll grab it from your website.
Sure. And Sia, you at Fraunhofer, you obviously work on many different projects. What would you say would be the next big application?
I agree with the points already made. We do get a lot of interest for like non-data center comms applications as well. Certainly biosensing, like Callum said. In terms of hype, maybe not volume, quantum computing. There's quite a few quantum computing architectures that are looking to do scaling based on PICs. Now that might not be the sort of customer electronics or customer devices volume, but certainly in terms of what you're going to hear about in terms of science moving forward, I think that's probably a big area.
Great. Well, we're reaching time, so Callum, maybe I can come to you with this last one. Is if someone leaves today after watching this thinking PICs might be relevant for me, what should be their next concrete step?
Can I shamelessly plug the PIC Bootcamp training course?
Please do, please do. Yeah.
Yeah, you should educate yourselves more. We've touched the surface in an hour. There's loads more to learn. Engage with training programs, attend trade shows that are relevant, just talk to people.
Sure.
That's my recommendation.
So we started on time and we'll finish on time. But the takeaway I would personally underline is that PICs aren't a silver bullet, but for the right problems with the right expectations and skills, they can be transformative. So sessions like this, like the entire PIC Bootcamp, as Callum mentioned, exist to help people make that judgment clearly. So please get in touch with the team at Cornerstone, particularly if you're looking to partner and use their Foundry services. But once again, I thank Callum, Remus, Sia, all of Cornerstone, and all of those involved in the PIC Bootcamp for sponsoring this industry tutorial brought to you by the great team around me at Optica. So thanks so much for attending, for your attention, for your questions. Bye for now. Thank you.